So here is the problem where you are given a test cross and the progenies obtained are given in the table. From the progenies, we can first find out the parentals and the double crossovers. So here capital A, capital D, capital R with 265 offsprings, and small a, small d, small r with 275 offsprings. They are the parentals. Offspring showing highest number, and offspring showing lowest number is capital A, capital D, small r, and small a, small d, capital R. The first one is showing 24 progenies and the second one is showing 16 progenies. So these are the double crossovers. So by comparing the genotype of the parentals and the double crossovers, we can find out the gene order. So while comparison, we see that AD gene here is same in the double crossovers. Small a, small d gene is also same in the double crossovers. And now we have found that the R gene is flipped. R gene is flipped. So R gene comes in the middle. So now we are going to rewrite this table so that all the R genes are in the middle. Then we are going to find out single crossovers at the region 1, single crossovers at the region 2. Then we are going to find out the recombination frequency, and based on that we are going to see how much is the distance between those genes. So now I have rewritten the genes in order. You can see the parentals, double crossovers, single crossover offsprings formed by the crossing over at region 1, that is between A and R gene, and at region 2, that is between R and D gene. Now we are going to find out the distance between A and R gene and the distance between R and D gene, and to construct a chromosome map. So to find the distance between A and R gene, distance between A and R gene. So for that we have to find out the recombination frequency between these genes, or we can call it as crossover value. So for that we write the number of recombinants that is produced by single crossover between A and R gene. So this is the single crossover offsprings, as you can see here. This is the single crossover offsprings produced by crossing over between A and R gene. So we write down the total number of those recombinants, that is 90 plus 70, and to it we add the number of recombinant double crossovers, because during double crossing over, the crossing over between A and R gene also occurs. So divided by total number of offsprings, we have computed it as 1000. Okay, now let us see how we get the result. I am just taking the calculator. So it is 90 plus 70 plus 24 plus 16 divided by 1000 into 100, because we express it as percentage, 20. Okay, now into 100. So we get the answer as 20%. And we conclude that the distance between A and R gene is 20 map units. Now we are going to find out the distance between R and D gene. So here also we find the recombination frequency, where we add the recombinants produced by single crossover at region 2. As you can see here, it is 120 plus 140 plus we add the number of double crossovers also divided by 1000, total number of offsprings into 100. Now let us see what is the value. 120 plus 140 plus 24 plus 16 divided by 1000 into 100. So the answer is 30. So the answer is 30%. And thus we conclude that the distance between genes R and D is 30 map units. Now we are going to map the chromosome. Let us draw a chromosome map. So I am drawing a chromosome. So let us imagine that this is the segment of that chromosome where those 3 genes are present. So you know the gene order. R is in the middle, A and D is on 2 sides. So we can write R, and the distance between A and R is 20. So we arbitrarily place R close to A, and the distance between R and D is 30. So we place D somewhat away from R, and we write the map units here. It is 30 map units. Here it is 20 map units. So this is how we map the 3 genes under consideration in a chromosome. So we have constructed a chromosome map and find out the distance between the genes. Now you have to find out the coefficient of coincidence. As you know, coefficient of coincidence is the occurrence of crossing over between the 3 genes at the same time. So it is calculated using the formula as you can see here. Observed frequency of double crossovers by expected frequency of double crossovers. So from the table, from the given data, we find the observed frequency of double crossovers, where the double crossovers numbers are 24 and 16. Dividing that by total number of offsprings into 100 gives us 4 as the observed frequency of double crossovers. Similarly, we find out the expected frequency of double crossovers, where as you can see the number 90 and 70 is single crossover recombinants at region 1. 120 and 140 is single crossover recombinants at region 2. And 24 and 16 are the double crossovers. We have seen these number of offsprings we have seen that these number of offsprings are recombinants, and we expect that at region 1 and region 2 double crossing over must have happened. If that had occurred, our expectation is that Total, these recombinants divided by 1000 into 100 is the frequency of double crossover. Expected frequency of double crossover, we get it as 46. Now, we can compute these values into the formula. Coefficient of coincidence. Observed frequency of double crossovers 4 by expected frequency of double crossovers 46. So these are all percentages. As you know, this is 4 percentage. This is 46 percentage. And by computing this, we get the value as 0.086. This is the coefficient of coincidence. So using this, we find out the value of interference. And it is 1 minus coefficient of coincidence, and we get it as 0.916. So we conclude that there is a 91.6 percentage interference which prevents the occurrence of double crossing over between A and R genes and R and D genes. So simultaneously, the occurrence of double crossovers is prevented by 91.6 percentage.